All right, so you ever like pick up your coffee mug and just wonder what keeps it from passing right through your hand?
Magic.
Well, I mean, we know it's not magic, right? It's
Yeah,
physics.
right.
And at the heart of it all is this thing called the Higgs field. And it's basically what gives everything, including you and me, and yes, even this coffee mug, its mass.
It's a strange thing to think about, for sure.
It really is. And we've gotten some research from our listeners about what would happen if this Higgs field went a little bit haywire. So we're going to dive into that today.
Sounds fascinating.
Oh, it gets wild. But before we get into all that, maybe we could start with you giving us a little rundown on the Higgs field, just so everyone's on the same page.
So, the thing about the Higgs field, it's not something you can just isolate and tweak.
Yeah.
It's like woven into the very fabric of the universe, you see.
So it's not like turning a dial up or down. It's more like pulling on a loose thread and maybe unraveling the entire sweater.
That's a great way to put it, actually. Even a tiny change in the Higgs field would set off this domino effect. And because everything's interconnected, even at the smallest level, those changes would just cascade outward.
Okay, so let's break down that cosmic domino effect a bit. Where does it start?
Well, it starts at the very foundation of matter. Particles like quarks and electrons. These are the building blocks of atoms, and they'd be the first things to feel the impact of a destabilized Higgs field.
So those quarks that make up, say, the atoms in my coffee mug here, what happens to them?
Well, their mass is determined by how they interact with the Higgs field. So if that field changes, their mass changes. And that throws off the balance that holds those particles together.
And when you say it throws off the balance, what does that even look like? Does my coffee mug suddenly become, like, lighter? Or heavier?
It's not quite that simple, unfortunately. It's not just about the mass changing. It's about the fundamental forces that govern how those particles interact. Those forces are also influenced by the Higgs field. So a change in the field could mean those forces become weaker or stronger or even behave in totally new ways.
Okay, so if those fundamental forces change, then the way atoms hold together. And if atoms aren't stable, then nothing built from atoms is stable.
Precisely. And that's where things get really interesting. And by interesting, I mean potentially catastrophic.
Yeah. My coffee mug is starting to feel a little less like a comforting example and more like a ticking time bomb.
Well, it's not just your coffee mug. It's everything. The buildings we're in, the air we breathe, even our own bodies. We're all vulnerable because we're all just collections of atoms held together by these forces.
I'm starting to think I should have finished that coffee before we started this deep dive.
Perhaps. But on a more serious note, the research you shared suggests that for a planet like Earth, with its specific composition and reliance on a stable atmosphere, well, let's just say the consequences would be quite dramatic.
All right, you've successfully piqued my curiosity and maybe stoked a little bit of existential dread. Let's talk about those dramatic consequences. What does the research say about how Earth specifically would be affected?
Well, think about what you depend on, like fundamentally, to exist, right? You need air to breathe.
Last I checked, yeah. This whole Higgs field thing is making me rethink some of my life choices.
Understandable. But imagine if that air that we kind of take for granted were to suddenly, poof, vanish.
Okay.
And I don't mean like blown away by the wind or something. I mean actually dissipate at the molecular level. Very real possibility if the forces holding those molecules together were to weaken or just disappear entirely.
So no more leisurely strolls in the park for me. Got it.
Right.
But Earth's demise aside, what about the bigger picture? What happens to, like, the rest of our solar system if the Higgs field goes on a rampage?
You know, it's fascinating. Our solar system is incredibly diverse when you think about it. You've got planets of all different sizes, compositions, colors even.
Right.
And the way each of those celestial bodies would react to a change in the Higgs field, well, it wouldn't be uniform, that's for sure.
So some planets get off easy, while others not so much.
Well, the source you provided specifically highlights the sun's fate, and it's not a pretty picture. Imagine for a moment that the star that sustains us, that anchors our entire solar system, suddenly wasn't there.
Talk about a bad day at the cosmic office. But how does that even happen? Does the sun just blank out of existence? Explode? What are we talking about here?
Two scenarios are presented, actually. One is a rapid collapse, the other a massive supernova.
A 2-for-1 cosmic apocalypse. Now, this is why I love these deep dives. Okay, so collapse first. Paint me a picture.
Imagine looking up at the sky, and instead of our familiar life-giving sun, you see, well, not much of anything at all. A black hole, you see, it doesn't emit light. It consumes it. So the sun's mass collapses in on itself. Its light would dim, then just vanish entirely, leaving behind a void in the sky.
Okay, so not exactly a visual spectacle, but the implications are definitely chilling.
Definitely.
But what about option two, supernova time? Give me the Hollywood version.
Oh, a supernova is definitely Hollywood-worthy. Picture this. A blinding flash of light, brighter than anything you've ever seen, engulfing the sky. It would be beautiful, terrifying, and utterly destructive.
Talk about going out with a bang. But destructiveness aside, how would that supernova affect the rest of the solar system?
It's not just about the explosion itself. It's about what comes after. A supernova unleashes an unimaginable amount of energy, and a significant portion of that energy is released as radiation.
And not the good kind of radiation that powers our phones, right?
Definitely not. We're talking about high-energy radiation that can rip through matter, disrupt atoms, essentially sterilize anything in its path. So even if a planet was far enough away to avoid being completely obliterated by the blast itself, the radiation would still be a death sentence for any life that might exist.
So basically, supernova or collapse, it's game over for our little corner of the galaxy.
In a sense, yes. But here's the thing. This isn't just a local event. A change in the Higgs field wouldn't be confined to our solar system. It would be a universal phenomenon.
Okay, so we've covered Earth getting, like, Thanos snapped out of existence and the sun deciding to go supernova. But you mentioned this isn't just a local solar system problem. We're talking like universal makeover, right?
Make bigger.
Bigger than a supernova that could wipe out a galaxy. How do you even get bigger than that?
Imagine this. It's not just stars and planets rearranging. It's the fundamental laws of physics themselves changing. The source calls this a phase transition.
Phase transition. You know, sometimes I feel like I barely passed high school physics.
Don't worry, it's a concept that trips a lot of people up. Think about water. It can exist as ice, liquid, or vapor. Same substance, but how it behaves completely changes depending on the temperature and pressure. That's a phase transition.
Okay.
Now imagine, instead of water, it's the entire universe. And instead of temperature, it's the Higgs field that's changing. This shift could cause the universe to transition into a completely different state, governed by a whole new set of rules.
So, our universe, with its galaxies, black holes, perfectly brewed cups of coffee, it's just one possible version of reality. There could be others, with their own set of physical laws, maybe even their own versions of coffee, who knows?
Exactly. And some physicists even think our universe emerged from a previous phase transition.
Hold on, a universe before the Big Bang? Is that what we're getting at here?
It's wild, isn't it? We can trace the history of our universe back to a fraction of a second after the Big Bang, but what came before that? What caused the Big Bang itself? A phase transition from a previous state of the universe is a leading hypothesis.
Okay, now my brain is officially in pretzel mode. So, if our universe was born from the ashes of another universe, what does that mean for, well, everything? Does it mean this whole cycle could just repeat?
That's where things get truly mind-bending. If the universe can undergo one phase transition, why not more? It suggests the possibility of a cyclical universe, one that expands and contracts, or maybe even transitions through a series of different states, each with its own set of physical laws.
So it's not just about the end of the universe as we know it. It's about the potential for endless beginnings and endings, a cosmic dance of creation and destruction that could go on forever.
It's a truly awe-inspiring concept, and it really changes our perspective on our place in the universe. We're not just witnessing the unfolding of a single story, but potentially a single chapter in an infinitely long epic.
We started with a simple question about what gives a coffee mug mass, and ended up contemplating the infinite possibilities of a cyclical universe.
That's the beauty of knowledge, isn't it? You never know where it might lead.
Well said. Big thanks to you for guiding us through this incredible journey. And to you, our listener, thanks for coming along for the ride. If you're still reeling from this mind-blowing exploration, and let's be honest, who wouldn't be, check out the show notes for links to all the research we discussed. Until next time, keep questioning, keep exploring, and keep that cosmic curiosity alive.